So last time we saw some definitions and some methods of uh, computational indistinguishability, which is less stricter than our perfect indistinguishability, but more useful in real life, since we are not going to be sticking to just perfect secrecy. Right? Perfect secrecy was really strong, in fact, too strong, and it became too limited by how strong it is. And we realized we don't need it to be perfectly secret. If we can bound ourselves by attackers who can only work in polynomial time rather than infinite time, and if they do just slightly worse, if the probability of success is just slightly worse uh, for those people, for those attackers, rather than needing it to be exactly one half, right? Another important concept in all of this is pseudo randomness. Okay, so what is pseudo randomness? Before we get to defining pseudo randomness, let us talk about why do we care about what exactly pseudo randomness is, or in fact, why do we care about randomness? Okay, so first of all, we need randomness in our definitions to choose a random key, right? All our algorithms so far have been saying, oh, choose a random key, let Jen choose a random key. However, in real life, we can't really choose randomly. Humans can't choose randomly. We need a computer to choose randomly, but even that is not really out there. We don't know if computers are going to be actually completely random. So what we rely on is pseudo randomness. It's close to random, and we don't know if it's actually random or not, but we believe that it is really close to random. Okay, so things like that are called pseudo random. We'll get to the proper definition. And pseudo randomness is a very important block for computationally secure encryption. So, important building block. Why do we care about this? It's an what the heck? Important building block. Important building block for computationally secure encryption. For computationally secure encryption. Okay, and it is a very, therefore it leads to being a very important concept in cryptography. Okay, but as we talk about what is pseudo random, right, which brings us to the question, what is random or what is uniform? What is uniform? What is random or uniform? Okay, and well, we are talking about random strings or uniform strings. Which of these following is a uniform string? Which of the following is a uniform string? Let's give some examples. 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, or 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, or 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Which of these is a uniform string? Now the thing is, uniformity is not a concept that you generally associate with strings. Uniformity is a property of the distribution. So if we generate a uniform string, if we generate a uniform, how many letters is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12-bit string. Each of these should have the probability, each of the above occurs with probability IO 2 to the minus 12, right? These are just one of the strings that, like, these are just three of the strings that you can make with zeros and one, from made of length 12, like of 12 bits, right? So all of these are uniform strings if my probability distribution is uniform. So uniformity is a property of the distribution rather than the strings, is a property of the distribution rather than the string, rather than of a string. Okay. Similarly, randomness is going to be a property of the distribution. Okay. Similarly, randomness is a property. Well, let's not go there. So we won't define random. So we will only talk about uniform distribution and pseudo-random distribution. So let me just stick to uniformity and things. Okay. Okay. Distribution definition. A distribution on n-bit strings is a function d, generally denoted d, from 0, 1 to the n to 0, 1, 0, 1. Okay, such that summation over x, distribution of x, is 1. So distribution is very much like a probability distribution. It's just asking what is the probability of this string occurring, or what is the, yeah, just think about it as the probability of one particular string being chosen. The uniform distribution is on n-bit strings, is the distribution that gives probability 2 to the minus n to every single string, denoted un, assigns probability 2 to the negative n for every x for every string x in 0, 1 to the n. So every n-bit string is equally likely to appear. So that is what a uniform distribution is. Everything has the uniform probability 2 to the negative n. Okay. So what is pseudo-randomness? What is pseudo-random. Pseudo-random. So random is more or less, in this case, what we mean by uniform. Okay? In this case, random is going to be uniform. So informally, pseudo-random is something that cannot be distinguished from uniform. So informally, it is something that cannot be distinguished, cannot be distinguished, GUI, from uniform, i.e. random. So whenever we say actually random, we mean uniform. Okay? Once again, pseudo-random is a property of the distribution. It is not a property of the string. Pseudo-randomness is a property of the distribution. Not the string. So if I give you the same three strings again, and I ask you which of these strings is pseudo-random, technically that question doesn't make sense. The string is not random or pseudo-random. It's the distribution which is random or pseudo-random. Okay? So notation. Fix some distribution. Fix some distribution. D on n-bit strings. D on n-bit strings. And then x by d means x, sample x according to the distribution d. Okay? So if I want to say with uniform distribution, it would be x by un. Okay? So historically, pseudo-random was something that passed us a bunch of statistical tests. D was pseudo-random. D was considered pseudo-random if it passed a bunch of statistical tests. If it passed a bunch of statistical tests, a bunch of statistical tests, i.e. Generally, if AI is equal to AI of x is equal to ith letter in string x, then the probability then it was considered pseudo-random if the probability of x of d, x by d, if AI of x is equal to 1 was the same as probability of x, which is the uniform probability of x is equal to 1 for every I is equal to 1 to 20. Okay, and these should be half. So probability of the first letter being 1 should be half, probability that last letter is 1 should be half, probability that the middle letter is 1 is half. But this is not sufficient. But this is not sufficient today. This is not sufficient today. Okay. Especially since we don't know what statistical test an attacker might use. Especially since we don't know what algorithm slash test an attacker might use, an adversary might use, right? And so we need to redefine pseudorandom. Okay, so definition. Informally, it should pass all statistical tests. Like it should satisfy all efficient statistical tests. Any efficient adversary that we have talked about before, as in it can only work in polynomial times, should not be able to tell if it's uniform or not. So, definition: let D be a distribution let D be a distribution on p-bit strings, p-bit strings. D is T epsilon pseudorandom if for all A running in at most time t, for A running in at most time t, the probability that x from D, that AX will guess 1 should be the same as the probability that X is on a uniform distribution and AX A guesses 1 for that string should be smaller than or equal to epsilon. Okay, so what does it mean? Let A be any adversary, okay, and he has to guess whether they design some test, right? They either output 0 or 1. Doesn't matter what their test is. Their test is going to take a string and output 0 or 1 based on the string. They might be testing for the parity. They might be testing for the digits. They might have some other criteria. Who knows? Whatever criteria they're using, they should almost be equally likely to say 1 for the uniform distribution as they are for the distribution D, in which case they're called pseudorandom. So what is informally? Informally, whatever test A uses, whatever test A uses, they should it should result in should result in output of 1 almost as with almost as much likelihood with almost for a string. Okay, for a string based on distribution D, based on distribution D, almost as likely as it would for uniform distribution. Okay, this is an informal take. It's not a very strict definition. We have already given the proper definition. Okay, and this is the concrete definition of pseudo-randomness. We saw that we can define it either concretely or asymptotically. So let us give it an asymptotic definition. Definition asymptotic. Okay, let me define the security parameter and stuff before first. Okay, so let n be a security parameter. So let security parameter CRIT parameter is equal to n polynomial p. Polynomial is equal to p. Okay, and then let Dn be a distribution. Distribution over Pn bit strings. Okay, and in that case, pseudo-randomness is a property of the sequence of distributions. Pseudo-randomness in this case is a property of a sequence of distributions Dn is equal to D1, D2, and so on, and the distribution the sequence of distributions Dn is called pseudo-random. Definition: Dn is pseudo-random if for all probabilistic polynomial time distinguishers A, there is a negligible function epsilon. There is a negligible function epsilon such that the probability that you obtain x for an x in Dn gives if x is equal to 1 minus probability that x chosen from the uniform distribution, x obtained from the uniform distribution, results in a result of 1 should be smaller than or equal to epsilon n, where epsilon n is a negligible function as discussed. Okay? And that's the asymptotic definition of pseudorandom. Okay? So why do we care about pseudorandom? Apart from being able to actually generate pseudorandom numbers, why do we care? What if we could generate random numbers? We had talked about the fact that, oh, we can use data that we have obtained before to look at completely uniform strings and stuff, right? You can collect high entropy data and in a way uniformize it to get a uniform distribution, right? The reason we care is because actually random data is hard to obtain. A pseudo-random generator takes this really small sample size of actually uniform data and creates pseudo-random data, okay, which is going to look random, but it's not actually random. But for any efficient attacker, it is almost as good as random. And the way it does it is using pseudo-random generators. Pseudo-random generators. So, which are called PRGs. Okay. So what is a pseudo-random generator? A pseudo-random generator, a PRG, is an efficient deterministic algorithm. Deterministic algorithm. Deterministic means given some input, it will always provide the same output. That expands a short uniform seed, into a longer pseudo-random output. Into a longer pseudo-random output. Okay? So it's an algorithm which is going to take some high entropy data that you have found that you have perfectly uniform distribution on. Suppose it is only the length that these strings have is, let's say, 32-bit strings. So you only have uniform data for 32-bit strings. You want more or less uniform data, uniform keys for, let's say, 64-bit strings, right? But you don't have the data. So you feed a 32-bit string chosen uniformly into your pseudo-random generator, and it's going to throw out what looks like a random string, which is 64-bit long. Okay, that's what a pseudo-random generator does. So it is useful whenever you have small number of true random bits, small number of true random bits, and want a lot more random looking bits. Random looking bits, right? Since it's a pseudo random, pseudo means false in case you don't know, it's going to produce not really random, but false random data, right? Pseudo random data. You want to use that pseudo random data for your experiment or whatever you're doing. So, how does this work in terms of an image? It takes some seed, goes to the generator G, okay, and then it throws out a much longer output. Okay, so it takes some input X, okay, which is processed by your G, and you get an output which we will call the GX, where now the length of GX is some polynomial of the length of X, okay, and we want this to be much longer than X, or at least longer than X, more than X. That is the idea of what we want from a pseudo random generator, okay. However, there is something that's going to happen. This is never going to be perfectly random, and here's a very major reason for it. So what G does is it defines a sequence of distributions. G defines a sequence of distributions D or which we will write DPN. Okay, so how is DPN obtained? DPN is equal to the distribution on Pn bit strings defined by choosing X uniformly first and outputting GX. Okay. Then note that the probability of a certain string showing up, okay, DPN, on a distribution Pn of some string Pn length string showing up is actually the probability that you have a n length uniform string such that g of x is equal to y, right? Because that is how you're going to get the string y of length Pn, and this is actually the summation over all x such that g of x is equal to y multiplied by the probability that you choose the string x from a uniform distribution. Okay, but if you have a uniform distribution, each string has probability exactly 2 to the negative n, and so this is probability that x such that g of x is equal to y times 2 to the negative n is equal to, well, the number of elements of the set X such that g of X is equal to Y all over 2 to the minus n. Okay? Note, most Y actually occur with probability 0. Most Y occur with probability 0. Probabi 0. So for example, suppose G outputs a string, outputs takes input, given input n, given input string of length n, G outputs a string of length 2n. Okay? Then each of the output strings, have probability have probability 2 to the minus 2n in uniform distribution, right? But if it is being thrown out as a unique string, okay, if it's a one-to-one function more or less, but via PRG, they have probability 2 to the minus n, right? If you assume it's a one-to-one function that given an length and string, it's going to produce a unique length 2n string, which is different from another length n string producing it, then there are still twice as many, sorry, not twice as many, there are so many more strings that are going to, it's a factor of square rather than twice. It's a factor of literally being squared of how many strings there are, right? And most of these are never going to show up. Others have probability 0. Okay? And so we saw, most of these strings are going to have probability 0. Examples. So these are some insecure PRGs. Okay, first let us do a really easy one. Let g of x is equal to 0, 0, 0, 0, 0. Okay, so given any string, it just outputs 0. What is the distinguisher? And does it really work? So analysis of the situation. Analys. So Um, consider D. So consider the algorithm A attacker, who does this. Um, output one, output one. If um, string, if the string you see S is equal to 0, 0, 0, and output 0 otherwise. Output 0 otherwise. Okay. Then what is going to happen? The probability of x from dn of a of x is equal to 1 is equal to 1. Right? Whatever string you throw in from your distribution via gx, I am always going to say, well, it's going to be 1 because that string output is going to be 0, 0, 0, 0. On the other hand, dn if x is equal to 1, the probability, sorry, not dn, this should be un. The probability of me getting the string 0, 0, 0, 0 is 2 to the minus n, and any other string is 1 minus 2 to the minus n, right? So the only time I'm going to get ax is equal to 1 from a actually uniform distribution is when I have the string to 0, 0, 0, 0, which happens in 2 to the minus n cases. Therefore, probability of x from the n ax is equal to 1 minus probability x from un ax is equal to 1 is equal to 1 minus 2 to the n is much better, much greater than epsilon n or epsilon or whatever, right? This is much bigger than epsilon, and this is not a good pseudo-random generator, therefore not a secure pseudo-random generator. Okay, let us look at another one. So let gx is equal to x, and then you add another bit, which is OR of bits of x. Okay, so is equal to x adjoint XOR xi. Okay, now this is much more secure looking, right? If I talk about what my historical algorithms are going to give, this is going to, this passes all the historical tests, tests. Okay, because what is going to happen? Well, your first x is actually random, right? So the data there is perfectly random, and for the last bit it is going to be either half the time it's going to be 1, and half the time it's going to be 0, based on the parity of the sum of all of your all of the string, right? Is this secure? Well, we already know what algorithm we can use. We know exactly what the string is. So uh, let A do this. Um, what format did I use? Output 1, output 1, if last um, bit is the same parity as sum of previous n bits, 0 otherwise, output 0 otherwise. Okay. So if it is the same as sum or XOR or whatever you want to say, if it is the same parity, then say 1, then what's going to happen? The probability that given a string of length dn, the experiment ax is going to succeed. Ax is equal to 1. Sorry, this should is going to be 1 because any string that this pseudo-random generator is going to pop out is always going to satisfy this condition. On the other hand, probability that a uniform string satisfies this is actually just 1/2. Right? Because half the time it is going to match up, and half the time it's going to be exactly the opposite bit. And so, therefore, probability of x to the n ax is equal to 1 minus probability from the n un ax is equal to 1 is equal to 1/2, which is again very big. So again, this is not secure. Okay. So now it begs the question that how do we create these? Are they good? In general, in general, as defined, PRGs are limited. PRGs are limited. There are very few pseudo-random generators as defined, equally strong, and they generally have fixed length output. They have fixed length output. Okay. And they produce the entire output in one shot. They produce entire output in one shot. Okay. In practice, what happens in real life is that PRGs are based on what are called stream ciphers that we'll look at. So in practice, PRGs based on stream ciphers. And what that allows us to do is can be viewed as producing an unbounded producing an unbounded an unbounded stream of pseudorandom bits stream of pseudorandom bits pseudorandom bits on demand. Okay, so instead of saying, oh, here's the data of length n, now I am going to feed it to you. Standard PRGs that we defined so far will always give you Pn, right? If you feed the data of size 7 and you know what the polynomial is going to be, P, then it is always going to be giving you size P of 7. So if your polynomial is 2x plus 3, it's going to give out 2 times 7, 14 plus 3, 17 length strings. PRG is based on stream ciphers. You input a string and tell them, oh, even though I'm inputting a length 7 string, I want a length 18 cipher or a key, right? So it will produce a length 18 key. If you want a length 19 key from the same original data that you have entered of length 7, you tell it, okay, I want a length 19 key. It will produce a length 19 key. So it is a much more useful thing. It's not fixed on, okay, this is what you want. Because the data you have, it might have fixed length. You don't want to be restricted by, oh my god, I only get this much length. You would rather want whatever length you want, right? So these are more flexible, and actually they're also built to be more efficient. And we will look at them later in chapter 7 if when we get to it. If and when we get to it, we'll look at it. Okay? Now, the big question actually is, do such stream ciphers exist? Do such stream ciphers exist? And the really real answer is we don't know. Okay? It depends on P not equal to NP. If P is not equal to NP, then we can say that, oh yes, there are these stream ciphers. Okay. If P is equal to NP, a lot of things fall. If you don't know what P is equal to NP and P not equal to NP is, that is fine. That's not going to be that's not something that we are going to be covering in this course, and it's not going to be really important. But the idea is we don't know if stream ciphers exist. Okay? What we do is we actually assume certain algorithms are PRGs. We assume certain algorithms are PRGs. PRGs. Okay? We can prove within bound that they are PRGs. Okay? we can prove under assumptions they are PRG PRGs, but we don't know if those assumptions are true or not. Okay, so that is the problem. If our assumptions, which are based on P is not equal to NP, are true, these algorithms are PRGs. If not, well, we might be in very much trouble. Okay, so where do things stand? Why do we care about PRGs? Why are things being looked at the way they are? So the important idea that we are chasing is still perfect security, right? Perfect secrecy. We are still chasing perfect secrecy, but we know that it has inherent limitations. So where things stand. We saw there are limitations. We saw there are limitations to perfect secrecy. You see why. In particular, the length of the key must be as long as the message. The length of the key must be as long as the message. At least as long as the message. Right? To relax to relax that to relax the notion of perfect secrecy notion, we introduced computational secrecy. Okay, and now how do we overcome these limitations? So question how do we overcome prior limitations with these new definitions, Well, here's the idea. Okay, recall one-time pad, which is generally we are going to short it as one-time pad, OTP. Okay, and how does it work? So you have a message which is of size some p bits. Okay, it gets XORed by a key which is also p bits, and you get a cipher text, which is also p bits. Okay, and now the question is, what happens if you don't have a way of generating secure, a good way of generating keys of p bits? Okay, and that is where you do pseudo one-time pad. Pseudo one-time pad. Oops. Pseudo one-time pad. What does pseudo one-time pad do? Well, the idea is going to be the same. right? We're still choosing the notion of perfect secrecy, and we know that this is more or less the optimal way of doing it, right? So this is more or less going to say the same. Ciphertext. This is again going to be p bits. If you started with a message of p bits, right? And you want to encrypt it with a key of p bits, right? However, what you do is you encrypt it with a pseudo key, p bits. How do you obtain the pseudo key? Well, you obtain a pseudo key by your pseudo random generator, which takes your input of real key of n bits. Okay. So, formally, how does this work? Formally, or not in terms of image. So sudo one-time pad, sudo one-time pad. Here's how it works. Let G be a generator, a pseudo random generator be a deterministic algorithm with g of k is equal to polynomial k. Okay. Gen 1 to the n outputs a uniform n-bit key. Okay, right? So generator still is a uniform distribution. So it outputs a uniform n-bit key, right? We feed this key k to which has a security parameter n. So this n-bit key k has security parameter n. Okay, security parameter is now fixed to be n. Okay, bit4 is my message space. Therefore, message space as 0, 1 to the power pn. Okay. Now my encryption algorithm, encryption using the key k of m, is outputs gk XOR m, and the decryption k of m outputs gk tensor c. Okay. Now, correctness is obvious. Correctness is obvious. Right? What is not obvious is security. Okay. And so next time we will try to show that this is secure computationally. Okay, so all of our calculations now are going to be computational security. So they're not going to be fully secure, perfect security, but they're going to be computational secure. Okay, we'll show that next time.